So the daily problem is IPO. If you want to pause and read it, now's the time. So this one's this is a problem where it's mostly about understanding it. Once you get it straight and once you phrase it correctly, it goes from being kind of what could potentially be a pretty muddled mess to quite straightforward. And that's what I'm hoping to do. So if you're feeling like doing a hard, if you feel like today's the day, then buckle up, because hopefully by the end of this problem will seem pretty straightforward. So the idea is we have all these projects, leak codes going public, and it's trying to complete a certain number of projects that have a minimum capital requirement and yield a certain profit. And it's important to note this capital requirement isn't actually a cost. So if we, let's say, completed project 2, it requires 1 capital, but we're gaining 2. We're not gaining 2, but spending 1 or anything like that. We're trying to complete, at most, a certain number of projects, and we have a certain amount of starting capital. And there's a couple different directions you could go with this one. Dynamic programming would be not the worst idea. And I think that would be a really good impulse, because you're trying to maximize your final capital. And anytime you see maximize or minimize, dynamic programming is really good for optimization. So like if your mind immediately goes there, that's a really good sign. Another thing about dynamic programming is you're sort of, there's the jargon around overlapping sub-problems and finding an optimal solution, stuff like that. But really what that's getting at is that you have these different states and these different choices that you're relating to each other. So you're saying at any given moment, you could do this or you could do this. And how does that affect later choices, and how do those later choices affect these, and how do you compare these? And you have to keep track of all of that. And that's quite a good impulse. And I think that's actually a great place to start. But if we run through that for a little bit, I mean, let's try. Let's say, okay, we have 0 capital. That one's easy. We only have 1 choice, which is do the 0th project. So now we have 1 capital. And look at that. Now we can do project 2 or project 3. Or I'm sorry, project 1 or project 2. Because both of them require the same. And so it's like, okay, well, how do we choose between these two? How does this relate to, let's say, later choices? If the length of these was like, instead of 3, it was 100. And you can kind of tell running through this example, okay, we have enough for both of them. One of them straight up yields more. We're always going to choose this. Even no matter what choices came before or what choices came after, you're never choosing this project if this one's available, because this is just the same thing, but it gives more. And even if this costed 2 and this costed 1, it's sort of the same as this costing 0 and these costing 1, where it's like, okay, well, what's our available capital? If it's 1, then the choice is not a choice. It's just like there's only one option at that state. We do this one, and then our capital's 1. Let's say this project costs 2. So in this situation where we've done project 0 and now we're looking, what can we do now? If this is the only thing that costs 1, this is the only thing available, then we do that. And then let's say, this gave 2, and now this costs 1, this costs 2. It's the same thing as before. Both of these are available. Even if, I shouldn't say cost, I should say require. Even if they have different requirements, the only thing that really matters is, are they available to us or not? And if they're both available, take the greater one. If only one's available, then your choice is made for you. That being said, starting with this idea of dynamic programming, you can sort of reduce this down and say, actually, this is kind of a greedy solution that we would want to look at if we're pulling on this dynamic programming angle, because we don't have some complicated multidimensional array of states and choices that we can make that lead into each other that we have to traverse through. We really only have one choice at any given moment, which is just what can we do, and what's the project we can do that's going to give the most profit. And that's really what we're going to do. We're going to find a way to efficiently say which one of these has the most profit, with the caveat that we can afford it. And with a lot of hard problems, you want to look at the constraints. So we can see we can do up to 10 to the 5th projects. There can be up to 10 to the 5th available projects. And that in mind, 10 to the 5th, we could have that be O of n. We could traverse through that. We can't have O of n if n is W, because 10 to the 9th is way too much to traverse through. So we couldn't do like a bucket sort or something like that. But what we can't do is O of k times n here. We can't just search through profits and say, what's the best one that also we have the capacity to afford? We can't do that. We can't traverse through this every single project that we pick. We have to find a better way. And that's where this problem gets potentially a little messy if you're not particularly confident in sorting, pairing indices and elements, priority queues, heaps, things like that. So that's a little bit what we're going to tackle. So the main idea here is we're going to sort capital. That's the first thing we want to do. But we don't necessarily just want to sort it, because let's say this was like 1, 2, 0, whatever, and it wasn't like this where it's already pretty much sorted. If we sorted this, we're forgetting that this leads to this 3, and this leads to this 1. So not only do we want to sort it, we want to pair these with their original indices and then sort that by the elements. So if this was, say, 3, 2, 1 instead of 0, 1, 1, this 3 would go to the end, but we would want it to still point to this 1. So we want this to be 3, 0, this to be 2, 1, and this to be 1, 2. And then we sort them, and then in the end we'll see, hey, this costs the least, this costs the middle, this costs the most, is what this kind of new sorted array of tuples would represent. So we want to sort it, but we also want to pair index with element. I'm actually going to say element with index, because we're sorting by the elements. So we kind of, if we're making a tuple, at least in Python, we want to have that be the first thing. So once we sort capital, what we're going to kind of do is keep a rolling index and say, what's everything that's available to us? So here it's already sorted, so it's a great example. We can say, well, W is 0, so we only have this. We only have this one project that gives us 1. So we do that, and then W is now 1. So now we just keep going up until either we reach the end, or if there was a 2 or something past here, then we're like, okay, these are all the things that are available to us. So we want to keep track of maximum, let's say maximum capital required project that requires the most capital. In the capital array that we're sorting. And then from there, we pretty much just do one project at a time. So we're going to iterate through k times and say, pick the one that's the most. So here that would be 1. And then we say, okay, great, now we have this. And then we're looking at these two because we've already done this one. We say, pick the one that gives us the most. It's this. And then if k was 3, then we would have done the other 2. And we say, pick the one that gives us the most of 2, which is this. And actually, the data structure that we exactly want for that is a heap. Or a priority queue. Priority queue is pretty much just a heap. You can kind of think of a priority queue. It's a more abstract data structure than a heap. A priority queue looks something like you sort of have like a flagging element and then the item, something like that. So you say this item has a priority of 1 and this item has a priority of 2 and so on. And then you can always pop the item with the most recent priority. So you sort of have a key and a value, whereas a heap is more just something like that, where you're like, okay, well, just this item is the lowest, so you can pop it. And I typed these in ascending order. A heap actually isn't sorted. A heap has certain properties. O of log n insert into a heap, and O of log n removal from a heap. But you actually only really have access to this 0th element. And it's not, the heap isn't sorted, but what is guaranteed is that the 0th element is the smallest. So if you popped everything off of the heap, it would take log n for each operation. and you would get the lowest element each time. So it's very similar to sorting, but it's not quite the same. So we want to store all these elements in here. We want to store all the available profits to us, and then for each project up to k projects, we want to do two things. We want to pop from the heap, pop the max profit project from the heap, and then increment this counter we have here to add projects with a higher capital requirement into the heap that then we can potentially pop later. And the nice thing about popping is then we're like, okay, well, we've popped 0, so now and then we'll push 1 and 1, these capital requirements in. So then when we pop from the heap later, we don't have to worry about popping this again. That's already gone, and then we just have these two. And then let's say we pop the second project 3, and then all we would have is the 2 in the heap at the end of this example 1. So let's kind of lay this out. Let's say something like capital equals, first thing we want to do is say sorted capital, but we don't necessarily just want this. We don't want to just say capital.sort because we want to retain, again, the original pointers to the original indices. So we're really going to say something like x comma I for I, x in enumerate capital. So, and then let's just say like print capital, return 0. Okay, so we can see when we print capital, this one, the sorting order is exactly the same. So we say the element 1 has the index 0, the element 0 has the index 0. This element 1 has an index of 1. This element 1 has an index of 2. This is also sorted, so it'll pretty much be exactly the same. But we do have it sorted. If we change this around and said capital is now 321, then it's going to say element 1 has an index of 2, element 2 has an index of 1, and element 3 has an index of 0. So now that we have that, we want to have a pointer for it. So I'll say I equals 0. And at this point, we might as well say, let's get n in there, the number of projects we have available to us. And then from here, let's say, okay, what's the number of projects we have available that we actually can afford? And so this is going to be our heap that we're pushing and popping from. And in Python, you can do something like, you can say heap push available 2. So you'd push 2 to this heap. And then if we said heap push available, let's say 3, in Python, this heap push, heap pop function always treats this as a min heap. So then when we pop this, it'll always pop the lowest. So it'll pop 2. So what we really want to do is have these be negative when we push them so that it'll pop the lowest, which means the greatest absolute value. So this is sort of in Python how you represent a max heap as opposed to the default, which is a min heap if they're all positive. So that's what we're going to do. So we'll say something like while I is less than n, so while we still have projects that we can push to the heap, and capital at I at 0 is less than or equal to w, so our starting capital, while the capital requirement, which again is this x, so the 0th element in this tuple, whereas I is the pointer to the index, that's the first element, we're saying while capital at I at 0, while a given project's capital requirement is less than the capital we currently have, then we say available dot append, and then we want to have the profit because we're going to be popping the maximum profit and adding that, and we actually don't even need anything else in this heap. So we can say something like available dot append profits at capital at I at 1. So we're saying, okay, take a given element, make sure that we can actually afford it, and then look at that element's index to how much that's going to give us, and then add that to the heap. and then I plus equals 1. And then also we need to call heapify available, because here we're just appending them to the end. And if we're appending them to the end, there's no sorted order. There's no guarantee that the 0th element will be the smallest or the largest or whatever. And actually, we want to make sure that the 0th element is the largest, so we're going to make all these negative. And then once we have that, then we can sort of just do the exact same thing, but now we can actually start doing projects, now that we know everything that's available. So now we've added this 0 project, 1, to the available heap. So then we can say something like while I is less than n, and, or no, we'll say something like for, I'm not going to say for I in range k, I'm just going to say this, like do this k times. And each time what we're going to do in this loop is do a project, which is pretty simple. So we're going to say w minus equals heap pop available. And this is a little bit of confusing lingo, but w is going to be our rolling profit, because it's going to be our sort of capital at any given moment, which is what it starts out as. So we can just kind of reuse this integer, and then we have to say, like, really what we're doing is we're saying add the greatest element, but because this is the smallest negative element, aka the greatest element, but we have it negative, we want to say minus equals so that we're adding it instead of subtracting a number. And then we pretty much want to do this loop again. So we'll say something like, okay, great, now that we have w's updated, it's greater than it was, like let's say the first iteration, we're going to add 1 to it, so it goes from 0 to 1, then add all of these. So we'll say something like, okay, while I is less than n, capital I at 0 is less than or equal to w, instead of saying available.append, what we really want to say is this time heap push the profit of that project to available. And then the final thing that we want to do is we want to make sure that we still have projects available to us, because there's a world where, let's say this costed 1, we have no way to do this. Or if these costed 2, okay, we could do the 0th project, our capital could go up to 1, but if these costed 2, we just wouldn't be able to do those. So the maximum capital we could get would be 1, even if we have extra projects left over. But this doesn't account for that right now, because it'll try to heap pop from an empty heap and throw an error. So we want to have something like if not available, return w. And then down here, we just want to return w. Oops. So if we print this, we can say, all right, let's print w. And what it's going to do is it's going to say, well, pretty simple here. Starts out at 0, and then we add 1. And oh no, actually it's because I changed this. So let's get back to this original test case. Starts out at 0, we add 1, because we're doing this project. So we add 1. And then the next loop, it's 1. We have things available to us, so we add 3. And then there's nothing more to add because I equals n. We have all of the projects possible are within our financial grasp. And then once we've added 3, we return that. So we return 4. And the last thing I'll say on the code itself is you could clean this up a little bit. You could say something like, actually, why are we this is pretty much the same as this. Why are we doing this twice? And right here, we could just say, actually, just don't even do that. And instead of doing all that, why don't we just say, hey, do this first, like add all of the available projects to the 2 available that we want, and then look at what we can do. And this also works. This is like a little cleaner, a little fewer lines of code. But the problem here, I'll go back in a second. The problem here is that heap push is O of log n. This is like a weird quirk of heaps. So if we have that the way that it was, we're heap pushing all of those initial elements. And here that's only one element. But there's a situation where, say, capital is greater than every single capital requirement. So we would be pushing all of them, and that would be nlogn to push every single element to the heap. Whereas here, we're appending them, which is O of 1, and then heapifying it, which is O of n. So that's actually O of n rather than nlogn, as far as appending things to the heap to available. It doesn't really matter because heap pop is log n, so already it's going to be like n log n of k, sort of, which is what this is. I mean, I would call this n log n, is what this whole, where n is the, I guess, minimum between k and the length of these, which is pretty fast. But it is a slight optimization to append these and then heapify, because this is O of n rather than n log n, to sort it into a heap. Whereas if we combine these, that would be n log n for those elements that we don't necessarily need to be n log n. So that's that. It works pretty well. Again, there's not really any grand algorithm here. It's just thinking about what it's asking. And I think like feeling empowered enough in your capacity to do things like this, sort something but retain the original information about the original indices, and using heaps and popping and doing like little things like this minus equals a negative number in order to have this be a max heap. If you don't get bogged down by that, then you can sort of have enough perspective to reason through what this is asking and how to do it, and see, hey, this is actually just a pretty straightforward, greedy question. But if stuff like this kind of gets confusing and is counterintuitive and you spend a long time debugging, then that compounds, and what is originally somewhat of a straightforward problem, when it's all said and done, becomes an absolute nightmare where you have 4 inputs and you're dealing with all these off by 1 errors and stuff like that. So I'll pontificate for a moment about, I think, like the takeaways for this, and then I'll call it. Once again, it's greedy because there's always one choice. It's always what's the thing that gives me the most profit that I have access to. And that's one way to think about why this is greedy and not dynamic programming. Another way that I think about it is, in a way, greedy solutions are dynamic programming solutions, because dynamic programming, you typically have something like an array, something like that, where you're storing some sort of information about a given state for every state in an input array. And then people talk about like 2D DP, where you have something like that, where you have this state of states, or you have this list of lists of states, for example, like Sudoku or some sort of traversal. You could have something like that, or more complicated string comprehension. And really, and you can have dimensions past this, like the sliding puzzle problem is sort of doesn't have too much of a dimensionality to it. It's just like non-dimensional states. But if you think about greedy, it's really like a 0-dimensional thing, where if 1-dimensional DP is you have an array that you're using to cache different states that you're traversing through, and multi-dimensional DPs, you have an array of arrays, or some sort of tensor or whatever that you're using to cache different states or different choices that you've already resolved. A greedy solution is just you have a number that you're using to cache all of the choices that you've made, which is exactly what we're doing here. So I like to think of it as 0D DP. And with greedy solutions and with a lot of things, it's worth thinking about what is the thing we're doing every time. And maybe another way to put that is, what's the loop invariant? That's a term. And technically what a loop invariant means is, what's the condition that holds true at the beginning and the end of every loop? So here, the condition that kind of holds true is, because we're doing this last, at every single point at the start and end of each iteration of this loop, all projects that we can afford are available to us. So pretty much the first thing we do in the loop is say, if nothing's available, then we're done. And if something's available, then pop it. and then we restore that loop invariant. That's one definition of a loop invariant. I think also, in more informally, a loop invariant is just not only what Boolean logical value are you holding true at the beginning and end of every loop, but also like what are you doing every loop. And realistically, what we're doing when we say w minus equals heap pop of available is doing a project. So for every iteration of this loop, we're doing a project and then adding everything that becomes available to projects that we can do. And I bring that up not only because that's useful nomenclature, but also because that's kind of the crux of a greedy solution is what's the thing you're doing? What's the choice that you're always making that's always optimal? And it's pretty much this right here. That pretty much explains it. Hopefully this was somewhat understandable. I'd say leave a comment if you have any questions about this. I feel pretty confident in juxtaposing greedy and DP solutions, and I think this is a great problem to start looking at hards, because it is hard, but it's challenging. It's not a gotcha problem. It's like workable. And this was my first video in quite a while. I've been studying very intensely, but got to get back on the grind as far as making these videos go. So let me know if this was helpful. Hit like if you learned something. Have a good rest of your day.